All right, we're back with now, what do those numbers mean when it comes to atoms and the periodic table in particular? So the first number we're going to talk about is atomic number. Atomic number is the number of protons. So you can see from these examples here that if we are looking at the number of protons, what we're really after is hydrogen only has 1 proton and carbon has 6. The other number that's not shown on here is the number at the bottom of these blocks of the periodic table, and that's called atomic weight, or formula weight of those atoms when you start to put them together into compounds. Those are things we'll talk about at the end of this lecture. Probably one of the most important features of this chapter, though, is realizing that atomic number, the number of protons, is the easiest found number. It's right above the atomic symbol of our periodic table. As we start to look at mass number, remember mass number is protons and neutrons only. So again, it takes over 1,800 electrons. So mass number again is the number of protons, which we call P positive, plus the number of neutrons, which is N0. It's kind of the abbreviations of those. So if hydrogen only has 1 proton, no neutrons, it has a mass number of 1. But there are hydrogens that have a mass number of 2 because they have an extra neutron. Same thing with carbon 12, it would be 6 plus 6. Uranium 92 can make uranium 238 by adding 146 neutrons. So notice the atoms get bigger because they have more subatomic particles, both protons, neutrons, and electrons in this situation. So how do we compare atoms then? If you remember from John Dalton's theory, he said that all atoms of a particular element are alike, but there are some that are different in the sense of what we can now call isotopes. So let's look at these 3 examples here. We have carbon 12, 13, and 14. So let's show you those differences. First thing we're going to do is Bush Stadium with a marble in the middle, another Bush Stadium with a marble in the middle, another Bush Stadium with a marble in the middle. So basically we have 3 atoms. Next thing we need to do is realize their names. This one we called carbon 12. And then we had a carbon 13. And then we have a carbon 14. So in order to be carbon, what we need is 6 protons. You have to have 6 protons in order to be carbon. If you change that number, you can't be carbon anymore. It's a very important feature. That's the atomic number. So the atomic number of protons, carbon is number 6 on the periodic table. So if you were to go to carbon and you would look for it, it would say 6 at the top. So this 6 is that 6. So basically they're marble-based nucleus, they're at least by analogy marble size nucleus, has got 6 protons, and that's what's unique about being carbon and not being any other element on the periodic table. What this also tells us is that out here in the stadium sits 6 electrons, because elements, at least so far in this semester, are neutral. Doesn't mean they always have to be, we'll see that later. But if you have 6 protons, 6 electrons, you're going to be neutral because 6 positive and 6 negative equals 0. Here's where things change though. If we have now a mass number of 12, we know that we already have 6. How do we get 12? Well, it also tells us that we're going to need 6 neutrons in the middle. And 6 plus 6 gives us our 12 mass number when we add them up. So for carbon 13, we're going to be a little bit heavier because now we're going to have 7 neutrons instead of 6. That's going to give us a mass number of 13. Notice in all these situations, we're not including electrons. Protons and electrons would determine charge. So in carbon 14, what we see here is we're going to have now 8 neutrons added to our 6 protons, and we're going to get a mass number of 14. If you look at the periodic table, you're going to see that it weighs about 12.01. That tells us that most carbon is probably this version. That's why the average that number represents is so close to 12 overall. And in reality, I think this is about 98% of carbon, about 1% is carbon-13, and then carbon-14 is actually radioactive, and about 1/1,000,000 of a percent of carbon overall. The last little math problem I'm going to go ahead and introduce is the one that's based on charge. If you have 6 protons and you subtract 6 electrons, you get 0. And when you get 0, that means you have no charge. And that's the case for all elements. You're going to have no charge. So as we look at this summary, kind of funny that carbon-12 has 6 protons, 6 neutrons, 6 electrons. Probably allows a little bit of insight to that superstition of a lot of scary horror movies, where the devil is inside of you, 666 is the devil. And notice most of our body's tissue is made out of carbon-12, which is 6 protons, 6 neutrons, 6 electrons. So maybe the devil is inside of every carbon atom, I guess, is where they get that idea from. What's unique about carbon-13 is that we're gaining a neutron, and in carbon-14 we're gaining 2 neutrons from carbon-12. These are called isotopes. So isotopes specifically have the same number of protons because you have to be the same element first, and then you have extra neutrons making you different isotopes, and they're very random. Not always are they perfectly, 12, 13, 14. They can be whatever they really want to be, and these are just a list of common isotopes of carbon. Carbon also has other isotopes, just not ones that are very abundant. So when you look at charcoal, when you look at graphite, when you look at diamond, which is all forms of carbon, they have this mixture. And it's not a mixture in the sense of homogeneous mixture because they're still the same pure substance carbon. It's just that every once in a while their nucleus has an extra neutron or an extra 2 neutrons, making it radioactive. So it's still a pure compound. Well, not pure compound, but pure element. They can make pure compounds like carbon dioxide or carbon monoxide, but that would be with subsequent isotopes, probably of oxygen as well. So it's a little more complicated than thinking that there are 118 elements. There's probably thousands of isotopes, because each element has several isotopes in many cases. So if we start to write isotopes, just recognize that the top upper left kind of number is called the mass number. That's the protons and the neutrons. So remember, this number is protons plus neutrons, whereas the bottom number comes from the periodic table, and that's just protons. So an easy way to find the number of neutrons is just to take these two numbers and subtract. When you subtract, you're going to get neutrons overall. So again, about 98 to 99% of all carbon is carbon-12. That's why it's so close to its average of 12.01 on the periodic table. About 1% is carbon-13, which is used in organic chemistry for identification, and then carbon-14 is radioactive. We'll see it in week 4 as an example of beta emission. Most isotopes don't make that big of a deal about their brothers and sisters that are so similar to them that we call isotopes, but hydrogen is kind of a big deal because what if your brother is twice as big as you? What if your sister is 3 times as big as you? Then it's a big deal because the percentage difference is a whole lot larger. So hydrogen actually has a nickname for hydrogen-2 called deuterium. We'll see that kind of sprinkled throughout the textbook, especially in the nuclear chemistry chapter. And then it also has radioactive tritium, used in watches for a long time to make them glow, so to speak. But again, very rare isotope, very radioactive isotope. This is the smallest atom, and it has the largest difference in mass when you add neutrons to it. So when you double its size, it is a little bit different in its properties than, say, its original. But when you think of carbon-12 to 13, you're only changing 1/13 of a fraction of its mass, and that's not near as detrimental to its physical properties as, say, doubling its weight or tripling its weight, as the case is with hydrogen. All right, so let's do an example. Here it says identify an atom with mass number of 16. So again, what do these numbers really tell us? Well, first thing we need to realize here is that we have a mass number of 16. So remember, mass number is protons plus neutrons, and that equals 16. Then they tell us that this number here, 9 neutrons, goes there. So some number plus 9 equals 16. That just tells us that 16 subtract our 9 gives us 7. So 16 is protons, neutrons. This is 9 neutrons getting removed from that 16 mass. That gives us our 7 protons left over. If we go to the periodic table, we're going to see that this is nitrogen. Nitrogen's number 7 on the periodic table. You get its atomic number down low on the lower left, and then on the upper left, we were going to get that mass number of 16. The charge here is 0 because electrons weren't mentioned. We'd assume them to be the same as protons, which is 7. I like to sometimes make a chart. Protons, neutrons, electrons. In this case, we have 7 protons that are positive, 7 electrons that are negative. And then we have the 9 neutrons that were given in the problem. If we had an atom, Bush stadium, marble, we'd have our 7 protons, we'd have our 9 neutrons in the marble, called the nucleus, and then out here we would have our 7 electrons in that stadium. Try another example. So here we have a full atomic symbol for 16 neutrons, atomic number 15. So if we were looking at atomic number 15, that tells us go to the periodic table, find number 15, and you're going to find phosphorus. Number of neutrons for 15 is based on what was given, that's 16. So if we take 15 plus 16, so this is 15 protons plus 16 neutrons, that's going to equal 31 mass number. So phosphorus has a mass number of 31, has an atomic number, which was given but also found on the periodic table, of 15. It has no charge because, again, electrons haven't been mentioned, and they won't be until the end of this chapter. Again, I like to make a chart to organize these ideas. We have protons, neutrons, and electrons. Protons were given in the form of atomic number, that was 15. Same thing, protons and atomic numbers. Neutrons were also given because they have to be, because there's so many different isotopes that are possible. So 15 and 16 make our 31 total for our mass number. Just like up here, you'll notice that that would have made our 16 mass number. And then our electrons, again, we're assuming are the same because they weren't mentioned. So that would just be 15 protons that are positive minus 15 electrons that are negative gives us a neutral 0 compound, which is in this upper right corner of our isotopic symbol. If we have Bush stadium and a marble, in that marble for this atom would be 15 protons because that's the atomic number given. In that marble would also be the 16 neutrons that were mentioned. And then sitting in the stadium watching would be the 15 electrons on the outside. And that's what we're after in this kind of chapter, to be able to do those kinds of problems. So here's a few more. List the subatomic particles present in lead. So when you do a particular problem like this, again, try to take away some of those clues of what we just talked about. Know that protons and neutrons together, that needs to equal 206. Protons themselves we can find from the periodic table. If you take that number and subtract it, so take 206 and subtract the protons, that should give you the neutrons. And then just by knowing the periodic table, we can kind of cheat, at least now, and know that that's the number of electrons as well, because these are neutral elements, not cations and anions that we'll deal with at the end of this chapter and all throughout the next chapter. Same kind of idea down here. It says chlorine 33. So again, go to the periodic table, find chlorine, and you'll find this answer pretty quickly. 37 is going to be the total of protons and neutrons. So if you take 37 and you subtract the protons, you're going to get the specific neutrons for chlorine's 37 isotope. And then again, just cheating for now, we can use the number on the periodic table to tell us electrons because we haven't changed those at all yet. So when we do that, we're going to see that, sure enough, lead's 82 on the periodic table. It's going to have 82 electrons. But 206 minus 82 in a calculator or your head, depending on what you want, is going to be 124 neutrons. A little bit easier math is chlorine. Chlorine is 17. Take 37 minus 17, you get 20. But because we have 17 positive protons, we're going to need 17 negative electrons, and that's what we see here for this example. Atomic mass is the last number that we're going to deal with, although we don't deal with this in the homework or the exam. I chose not to do that because the answers are already given on the periodic table. Atomic mass is the weighted average of all the isotopes that exist for that particular element. So weighted average is something that we'll have to talk about. Relative mass is based on carbon-12. If you take carbon-12 and you divide by 12, we get 1 atomic mass unit. That's a definition that's shown here on the slide. And then they use carbon-12 just because it's so common on the surface of our planet. So if we look at the weighted average of a simple example like Olympic shot put, in the men's event they use 16-pound shot put balls. So what we're going to do here is take that number 16 and then realize that if we multiply by 0.75, which is the 75%, we're going to get 12 pounds on average. If we do the same thing for the women's event, their shot put balls weigh only 8 pounds. So we take 8 times the 0.25. We're going to get a quarter of 8, which is 2 pounds. Add that together, we get 14 pounds as a weighted average. You have to be careful when you do this because if you were to do a normal average of 16 plus 8 and divide by 2, you get 24. You could divide by 2, you get 12. 12 is not 14. 12 pounds would be the simple average. And that's not what we want. Simple average is based on a 50-50 percentage where there's equal weight of the numbers, kind of like on your average of your exams or something. Here what we want is a weighted average, so we're using their weights, their abundances, to determine their percentage of mass that contributes to that weight. So because there's more men's shot put balls available than women's at these events, if you have a crate of 100 of those, it's going to be heavier than the average of 12 because 75 of those are 16 pounds and only 25 are 8 pounds. So this is the kind of number here that we want. This is called a weighted average. And that weighted average is what's on the periodic table. If we were to do the same thing for silicon, we do the exact same thing. We take these masses of 28, 29, and 30 for silicon, very abundant on beaches, in the form of sand, silicon dioxide. So here we have our mass of 28, 29, and 30. You multiply by the percentage by moving back those decimal points 2 places. So you're going to add a 0 there, you're going to add a 0 there. When you do that, you're going to add them up. And when you add it up, you'll see that this number here is within rounding error of the periodic table. So lucky for us, the entire periodic table has been done that way. So we don't have to do it separately in the homework or the exam. You're welcome. So in the end, what are we looking at? We're looking at is in the end, this top number being protons. The symbol gives us our abbreviation of the element, either by Latin terms or English terms, either one. The atomic mass, though, is a weighted average. And because it's a weighted average, we have to worry about all proton and neutron combinations. So this is a number. Protons is just a number. This weighted average, that's a calculation. So you can't use this number as a mass number because a mass number is just a number. So be careful. That's the biggest mistake that students make. They think that this number is a mass number. This number has a decimal because it's a calculation. So try not to think of mass numbers in this way because that's the biggest hang-up students have in this particular chapter and concept. So we'll pick up next time with the periodic table.